Hello, everybody, and welcome to today's webinar presentation titled Building Leaner, Faster Microservices with Embedded NoSQL, brought to you by FairCom. I would like to introduce you to today's presenter, Shane Johnson, the head of marketing at FairCom. Shane is a former Java developer and architect specializing in distributed systems. Prior to joining FairCom, he led technical marketing for Red Hat, followed by product marketing at Couchbase and MariaDB. At this time, I'd like to pass it off to Shane for his presentation.
Thank you and welcome everyone. Today's topic is microservices, which is a fairly popular topic these days, but I'm trying to approach it in a slightly different way than we have in the past. So hopefully we can cover some good material here. Let's do a little quick recap for the agenda. I'm going to give you just a very brief introduction on FairCom DB. It's not really the primary topic for today. And then we'll also do a little bit of a primer on microservices. There's a lot to say about microservices, and we could probably dedicate an entire webinar just to that topic, but I just want to do a primer, right? Some highlights, some key points that are going to be relevant for us today. Then we'll talk a little bit about database architecture, embedded versus client server, or hybrid. What does it look like to do both? We'll then kind of take that up a notch to start evaluating what production architectures might look like. And then we'll wrap things up by doing a demo. So I'll have more details on this here shortly, but I built a small microservice with FairCom DB using our NoSQL API. So I'm going to fire that up, walk through the code, make sure it works okay, knock on wood, and then we'll make sure to save some time for questions at the end. That being said, what I've tried to do is to get in a habit of making a sacrifice to the demo gods, especially when I'm going to do a presentation involving some code. And I pick a different one each time. It shows a little bit about my background. And this one, definitely, like some of the others, kind of one of my childhood favorites was Garbage Pail Kids, which I'm probably dating myself here. I think that package on the left, that's one of mine. I took a package of it. I think it's dated 1986, most likely. The one on the right is probably the quintessential card, which I don't believe that I have. But that being said, I do think I have Nasty Nick, or did when I was young, and the same is true for Frying Ryan. I always thought these were hilarious. I did when I was probably 7 or 8, and quite frankly, I still do today. So that's going to be our sacrifice to the demo gods. Hopefully they reward us with a nice smooth demo at the end of today's webinar. So that light intro into FairCom DB. It's a database written in C, and I'd say that the background, kind of if we look at the beginnings of FairCom DB, it was oriented towards embedded use cases, particularly in mission critical applications where there wasn't a great deal of computing resources available, and sometimes not even database administrators. So it needed to be really efficient, really reliable, and kind of self-correcting, if you will. But if we fast forward today a little bit, what I think is really notable about it is this stack of APIs, if you will. At the very bottom is our low-level C API. That's really for hardcore C engineers that need to get every last bit of performance out of FairCom DB, and to a certain degree even transform it into whatever type of database they need. So we kind of start to move up the stack a little bit. You have ISAM, and standard database APIs, and then in the little blue layer is a Rio API, and that's our record IO API. I've been building a Java prototype for this, which I'll show you guys a little bit later during our demo. These APIs are really oriented into embedded use cases. And then you have SQL, and then even REST, and currently in development is a JSON RPC API. So depending on where you're in the stack, whether you're taking advantage of an embedded, or you're doing server side, or even front end development, there's an API available to you. And it's a little bit different because it's a NoSQL database, but still really a relational model. And SQL actually came much later. So first it was NoSQL, and then a little bit farther down the road we added SQL. And of course, all the standard things you'd expect: transactions, encryption, replication. It's all there. The key points for today is really the NoSQL API, which we'll look at in the code, being deployed as an embedded database, within applications, or in our case, within a microservice, and the replication capabilities, which kind of help tie things together. Now on to our microservices primer, and this might be a little bit opinionated from my point of view, but I think most people agree is we're really trying to take larger monolithic applications, probably very big web applications today, and break these down into a set of independent services. And by independent, I mean they have no relationships, no direct relationships between each other's, hopefully no external dependencies. You can scale one without scaling the other. And I think if we maybe move away from the technical side just for a minute, ideally we think of these microservices as being application components, right? Even if we had a modern, even if we had a monolithic application with a good architecture, it's probably still fairly modular, right? It's still easy to identify the components. Now we're just kind of pulling these out, apart. And many times, and even some of the examples I'll use throughout this webinar, I also think of it as kind of vertical slices of our application. Usually I kind of refer to e-commerce applications. So there's the shopping cart slice, or the product catalog slice, the customer profile slice. And from a communication standpoint, largely HTTP, or in some cases messaging. The microservices platform we'll use a little bit later has integrated messaging if you want to do kind of reactive async, style services. And I'm sure there's some other options out there, but from a simplicity point of view, most of them are going to fall in this bucket. But I think where microservices haven't quite reached maturity is when it comes to the database. And I started hearing questions about this, not just previously at MariaDB, but even at Couchbase before that. As our customers were starting to pivot into microservices, they were kind of coming back to us and saying, what's the best way to handle the database as we refactor our applications? And in an ideal world, what I would want to tell people is that you want to avoid, kind of the standard big database, right? The one with tons of schemas and tons of tables, and it's your ultimate source of record. And what we'd rather have is a database for each service. If there is a customer profile service, it has a database with the customer profile tables. If we have a product catalog service, it has a database with all the necessary product related tables and so on. But there's a few challenges around this. One might be, how do we manage all these databases if, and it's kind of implied here, we're talking about traditional client server databases. So right now you have a DBA or a team of DBAs. They're managing a number of databases, and if you decided to decompose those, and now you had dozens of databases for them to manage, that can be a challenge. And yet, from a transactional operational point of view, we want to move away from kind of the big giant monolithic database. We still need an aggregate view of the data at some point, whether it's for BI and reporting, interactive analytics, data integration, chances are that even outside the transactional point of view, we still need that. So how do we deal with it? So we kind of start off with what I would think of as the traditional approach. And yes, we're oversimplified here from a diagramming perspective, but we have an application server. We have web applications deployed to it. And most of the time, regardless of your language, you probably have some sort of ORM framework in place. I come from a Java background, so that's JPA and Hibernate. You have your database driver, and then a second level cache. So for your Java guys, it of course come from Red Hat. That meant Infinispan as part of JBoss, or what I think it's Wildfly today. Which kind of have these three pieces working together, and then of course you have your data model, and these might still be services, right? I mean, you might still have a products REST service and accounts REST service running within your web app, and then a remote database server off the side with all of the tables. The thing about even this traditional approach is there are some downsides to it, even though we've been doing it for a really long time. There's network overhead, by sheer virtue of having to go across the network to get your data. There is resource contention when you have one database that's serving many applications, many services. And usually the result is kind of a brute force approach. We need to throw more hardware at it. Bigger servers, move to clustering, replication, go distributed. And then there's also kind of issues around availability and risk. Because if we went back to the perfect world, my microservice has no external dependencies. Yet in this model with a remote database server, it in itself becomes the dependency. If that database server goes down, my microservice stops working. Or things that we didn't anticipate. Someone accidentally sends a bad query to the database and now it's spinning, right? Someone did a select all on a massive table. It shouldn't affect you, but it is, because it's not only an external dependency, it's a shared dependency. And there's other issues that could come up, right? The schema not matching the application model, and so on. There is some inherent complexity, right? Even though app servers do a good job of wiring everything together for us, there's still a lot of moving pieces. And if we are doing our own caching on the client side, how do we ensure that that cache is synchronized with the database? Because we're not the only ones writing to that database. And then there's the notion of SQL in and of itself, which has kind of a bit of performance overhead because, and I say this in the context of simple CRUD queries, right? The things that we see a lot, even as consumers, right? When I'm on the website, I'm browsing a product catalog. I'm clicking on products to view more details. Maybe I want to go see the reviews or the ratings, or it leads me to click on related products. I decide to buy something, create an account, add payment information. These aren't complex queries. These are not analytical queries. Yet, you're going to have to go through the SQL parser, SQL optimizer into the SQL executor. The other aspect is that it's essentially batch oriented, because it's kind of a request response model where I kind of describe to the database what I want, send it over. The database does a number of things, right? It's not a simple task, but it does a number of things, and then finally it gets all the results together and sends them back to me. And I think when we start to think about embedded databases, it doesn't necessarily make sense anymore. We don't have to go across the network, so why do we have to use a batch-oriented paradigm? And certainly there's limitations and constraints within the language itself. I mean, SQL is great, it does a lot, but when you find yourself in a situation where you can't make it do exactly what you need, then you start to get a little bit more stuck, if you will. Do I force it? Do I do without it? Do I do some stuff in my app logic and some stuff in SQL? So it's always not always the best fit. So the approach that we would bring forward is the use of a hybrid, embedded model, where each of our three microservices has its own embedded database, and that embedded database has only the tables that microservice needs. And as a result, that microservice owns those tables. So we would say in this diagram that we're looking at, nobody should be making changes to the accounts table unless they're going through the accounts microservice. Nobody should be changing our product catalog unless they're going through the products microservice, and so on and so on. So they have sole ownership for all rights to those particular tables, and they're happening to an embedded database. There's no network, right? There's no overhead. There's no resource contention. Because they're local, they're probably actually cached in memory, right? Through either the OS page cache or some other approach. So it's gonna be super, super fast. And then what we do is we have each of these embedded databases replicate to that central database server in the backend. And so we start to get a little bit of the best of all worlds here. Each of these transactional microservices is operating as fast as humanly possible, right? Because they're working on an embedded database, which even if it's running to disk, it's still operating from memory, just because it's much smaller. If you have really big databases, yeah, I couldn't squeeze the entire database inside of a microservice. But if you're going to tell me that of that database of 1,000 tables, my microservice only needs 1 or 2 of them, those I probably can actually keep cache in memory anyways. And at the same time, that database server in the background, you can point your BI and reporting tools towards it. And what happens there doesn't affect those microservices, right? So a rogue query, a complex analytical query, even someone who accidentally corrupts the data, whatever happens there, it's happening independently, right? Those microservices, they only care about their embedded database. That's their source of record. And the replication can be asynchronous or synchronous. It just depends on the requirements. And so there's a few more things I would call out here is that in this type of approach, you have a couple different options. And we started to touch on it in terms of replication. And I meant to invert these, so I apologize for the typo. But if we were, for example, in the cloud with ephemeral storage, I'd probably do synchronous replication, despite my slide saying async. If I had persistent storage, then I might do asynchronous replication. That would be my opinion. The other way to look at it is the choice between memory and disk. So if we have the database server kind of off to the background, serving as kind of our aggregate of all data, and it's disk-based, I could potentially have my embedded databases be in-memory databases, especially if the data fits and it's going to be super fast. We have synchronous replication, but it's not a requirement, right? You could do disk-based both in your embedded use case within the microservice as well as a database server. And the other thing is when you have an embedded database within your microservice, you can use a database API. We don't have to do a SQL-based approach. And the way I kind of think about this is if I have an embedded database, and let's assume my working set fits in memory, because it's probably fairly small, tables are essentially in-memory lists. So I don't necessarily need to send a query that goes through an optimizer and a parser and so on and so on. I could theoretically just iterate through my list and kind of do my own filtering and do my own sorting. I probably wouldn't do that all the time. I'd still create indexes, but it's just a fundamentally different paradigm that when you're an embedded database, you shouldn't be doing kind of, and encourage you not to think in this request response, SQL query, SQL result mindset. That mindset stems from us having remote database servers. So it only makes sense to batch all the work up. But when your data is local and immediately available to you, you don't necessarily have to think that way. You can iterate over your tables. You can even iterate over results. So maybe you do have some indexes, but you don't necessarily have to delegate everything to SQL anymore, especially in languages like Java when you have the Streams API and you have all these ways to do sorting and filtering and mapping. You probably want to be able to take advantage of those more and more. And so a little bit about the database APIs, and we'll try to pull some up here in a moment, is they allow you to basically call functions within the database directly, as opposed to going through kind of a client server approach and protocol, and even kind of, how do I think about serialization, to a certain degree. But you're tapping the running database and telling it that you want to create schema changes, create tables, create indexes. You can specifically specify when to start a transaction, when to end a transaction. You can lock records manually or tables manually. And of course, you can perform all your CRUD operations as well. And I use CRUD as a little bit of a broader term to also include things like filtering or searching. So all this stuff is now done with functions and with objects, right? Native functions and native objects, to be clear. And it's more of an imperative approach rather than declarative. Now, you can still use those APIs to pass in a SQL query. You're not prohibited from doing that, but it may not be as efficient, and it may not really be the preferred option. As I mentioned before, I'm particularly interested in using the Java Streams API to begin exposing tables, because I think that's far more interesting to me and gives me more room to do stuff than if I'm leaving myself confined to what SQL can do for me and give back. So we get rid of the network overhead, we get rid of the network, we get rid of the resource contention. I say operate in memory because every database does its best to keep data in memory. Even persistent databases that write to disk, they go through page buffers and OS buffers and kind of internal mechanisms that they want to do as much as they can from memory. And in our microservices approach, if we're working with just subsets of what was originally a very big database, there's a good chance those subsets will fit in memory, or at the very least that the working sets will fit in memory. And the way I would describe it is that we are more or less pushing the transactional workload away from that shared central database and out to all of our different microservices and their embedded databases. And in a sense, it is a little bit like distributed in so much as you're not trying to use one really big machine to handle all your data access. Instead, you break it up and you let lots of smaller machines handle it. The difference, versus distributed, is all those little instances can work independently of each other instead of having to work together as one big database. From an availability and risk point of view, I could argue the data is always available and there is about as close to zero risk as you can get. Because when you're embedding databases and microservices, you're really loading libraries, right? And calling functions within those libraries. So it's not quite like a database server where you have lots of running processes and dependencies, and when the database server goes down, we hope that automatic failover will take care of things, but still it's going to be a pretty big impact. Versus when you're using embedded databases, they're more or less compiled within your application. They're more likely to fail than any other part of your application is likely to fail and bring it down. And part of the reason for that is there are no unknown queries. So when you build an application, or in our case here today, a microservice, and you embed the database within that microservice, the only queries that database runs, whether through an API or a SQL statement, are those defined by your application because it's not shared anymore. You don't have to worry about queries and calls coming from other applications or other microservices. They only come from yours. So you know how it's going to be used. You know how the data is going to be accessed. You know how much data there is. You know, all of these knowns, if you will, eliminate that risk. And you have fewer components. And you'll see this in a minute when we pull up the demo. Before we had to have our database driver, an ORM framework, and a second level cache. All of those things go away. All you have now is a client API interacting directly with an embedded database. And you don't have to use SQL. And data access is much, much faster and much, much simpler. And I think it also gives you the ability to take advantage of more language-specific features when it comes to working with your data, instead of having to, you know, in a sense, dumb it down, where my application code, all it really does is send a query, I get my results back, I serialize them to JSON, and I return them. So there's not a lot of opportunity in the middle there. But if we're using an embedded database, and we have NoSQL APIs, it's an entirely different story. So let's kind of take it up a notch. Those are kind of some of the concepts and principles, but what would it look like if we went into a production environment, which might be a little bit more complicated? One of the things that I think we don't always realize, embedded databases like FairCom DB can replicate to each other or to other database servers. And the choices are the same. Just if you think for a moment that you're not embedded, right? If you're, pick a database, out of a hat, in your production environment, you're probably using replication or clustering of some sort. And like always, the DBAs have to choose, is it primary and secondary? Is it asynchronous or synchronous? Are we gonna do clustering or bidirectional? You have all those same choices when you're using embedded databases as well. And I think what ends up happening in a production environment is our embedded databases, they're doing essentially all of the transaction processing. So if you're doing a customer-facing set of microservices, e-commerce, for example, all those e-commerce transactions, it's all happening through the microservices. The database server in the background probably just limited to things like BN reporting. In backups, another good use case, we don't have to do those on our live microservices. We can do those on the database server in the back end, and data integration, right? A couple good examples. So it looks a little bit like this. And I kind of picked two examples of microservices here. I only have so much room on the slide, but we have an accounts microservice, and we have a purchases or orders microservice. And there's three of them, three for each for high availability. So the way we start out is I would have these FairCom DB embedded databases replicating to each other. And here we just did bidirectional replication, or many-to-many, clustering, depending on how you want to think about it, which would allow us to kind of round robin our requests to any instance of a particular microservice. But it could be primary replica, in which case you might, route writes, say puts and posts to microservice number 1, and then load balance, any gets to microservices 2 and 3. There's lots of options there. But for this one, we'll kind of go this approach. And then we'll start up an instance, or 2 or 3 of FairCom DB server in the background, and then we will configure each of the embedded databases to replicate it to it. So what I chose in this particular example is synchronous replication between my embedded database instances. And it's kind of giving me that HA and durability that I'm looking for, and asynchronous replication back to the database server in the background. So each service has a small subset, right? You have the account services, they have an accounts table. I'm sure there might be a few more tables you needed. Same thing on the purchases side, you might have orders and line item tables. And then the FairCom DB server at the bottom has all of those tables, right? That gives you kind of the unified presentation. I really like this model because I could handle failure almost anywhere. So if any one of my microservices fails, it's not really a problem, right? I still have the other instances running. I'm still having data replicated to that backend database. And in my example, I kind of split it up a little bit farther. I had different proxies, or API gateways in front of these microservices because I really espouse a point of view where everything is, completely decoupled and independent. Any part of my microservices to be, bound to another, for one reason or another. And even the proxies, right, are kind of loosely coupled and independent of each other. And as I had mentioned before, I probably would, have backup and restore processes running on the FairCom DB server in the background. I don't think there's much value in running them on the microservices. Yes, we're doing asynchronous replication, but that's the nature of backups. Right? I mean, if there's data changing all the time, there's no perfect time to do a backup. So run those in the background. All our BI reporting tools, they can be running it, in the background. And it just leaves all of the resources on the microservices to be dedicated towards transaction processing. From a routing point of view, I found this to be really interesting as well, because in my past lives, database routing has always been fairly low level. Either you have database proxies or it's actually built into the database itself. But I think in terms of microservices, it allows us to move that routing a little bit higher up. And then we can actually start to do REST-based routing. And I hinted at this before, but we could say that all, post HTTP calls go to a specific instance, while any gets are load balanced to other instances. You could go even further. We might have, for example, an inventory microservice. We might then choose to split that microservice into many more microservices. Maybe we want to maintain inventory at a per region or per state, per district type of locale, and then we can use the URL to help direct it to the right microservice. So example, an inventory update might require the use of a URL that includes a store number in it, or a district number, or a region label. And we can also take advantage of session pinning as well. So typically in the database world, when you're in a primary, I'd say maybe kind of a clustered, multi-mastered, approach, and you're using asynchronous replication, there's always some concern of could you be getting stale data. But when we look at it from a microservices point of view, and we're thinking about HTTP connections and kind of web servers or load balancers, we could probably use session pinning to avoid that. And I think the final thing I would say is I start to think of microservices being more of the edge now, so to speak, from a data perspective, right? We've always thought that data was supposed to be consolidated, kind of in the back end somewhere, and everybody shares it. But this is really an inverted approach where, no, let's push the data all the way to the application, wherever it may be running. And then, of course, those applications and microservices, they can be pushed out really, really far and as close to the user as possible. So there's a little example of that, right? In this case, I might not do bidirectional replication anymore. I might choose, unidirectional primary replica type of approach, where microservice number one handles all of our HTTP writes. It then replicates changes to microservices 2 and 3, which are handling the HTTP reads.
And that could be synchronous if I want to avoid any stale reads, for example. And then I might also choose to replicate it, then to the FairCom DB server in the background. So this one's a little bit different. In the previous slide, we had all of our embedded databases replicating to, a shared database server in the background. We could opt for a topology like this, where only the primary microservice is replicating to the database server in the background. And a few examples of how we could start to play with the URLs. So I might want to have different microservices based on region. So one is running in North America, one in Europe, one in APAC, and we can use replication filtering to minimize that. So even though there's one very big accounts table in the server at the bottom, each of the accounts tables that's embedded in our microservices is actually just a sliver of that. So we're able to decompose our table even smaller, increasing the chances even more, of course, of it fitting in memory. And so now we get to the demo. As I mentioned a little bit earlier, my background's in Java, so that's what I used for our demo here. And I'm using Quarkus, which I think is really neat. And I won't say too much about it because that's probably an entire webinar topic on its own, but I'm using it as a microservices platform. You can use Maven or Gradle. I'm using Maven, and it's pretty neat because it can actually, it can build a runnable jar. It can also build a native executable. So it's very, 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 very fast. And this project, by the way, is hosted up on GitHub in the FairCom Labs account. Everyone's welcome to check it out. There's a README, fairly straightforward. I'm also working on open sourcing the client code that I'll show you today as well, and getting those clients published to Maven. So that's a little bit of a work in progress. Looking forward to that. And I'll point that out. So, bear with me when you look at my resources and you're thinking to yourself, Shane, why do you have, some of these jar files in your resources directory? It's because they're not on Maven just yet. But like I said, hopefully pretty soon. So I'm going to go ahead and switch to IDEA, which is what I use. So hopefully this is still sharing for everybody okay. And I have a fairly simple Quarkus project here. And maybe I'll start with some of the resources. This ctree jtdb.jar, this is the FairCom DB Java client. I think we can kind of look at it a little bit. Start to see kind of the different classes, databases, records, indexes, sessions. This FairCom DB client Rio, this is a newer Java client that I'm working on to try to provide developers with a more simplified approach to working with FairCom DB. This DLL file, ctdbs.jni64.dll, this is the embedded database library. And I believe it's about 4 megabytes in size. There's a 4 meg version and an 8 meg version. So that's the DLL that we load to get access to our embedded database. And then these two jar files are the Java APIs I'm using to call those C functions in our embedded database. There's a little configuration file, which I haven't done anything interesting to change that. There's a developer license file in here. And then there's a few application properties that I'm using to right now kind of control log messages. And there's this little properties file that kind of tells us where our FairCom DB configuration file is, where the license file is as well. So that's a little bit of what's happening in the resources. And then I'll come up to the code here, and I'll start with catalog app. This is just your basic application class, right? And we really just used it to add the application path annotation to create the /catalog path in our URL, which we'll open up in just a second. And then I have this database class, which is a singleton, and it has two things. One is the engine, and the engine is exactly what it says. This is our embedded database engine in this microservice. And the other one is an annotated session. So there's a couple different types of sessions that I'm working on. The one I'm showing off today is the annotated session, which kind of helps with object mapping. So this singleton, we get an instance of the engine, we start the engine, we get an annotated session. Now I just did this kind of quick and dirty for the purposes of a demo, but if there is no DB catalog database, we'll go ahead and create that database, and then we'll go ahead and create a table to store our book information. And then I have 9 books that we go ahead and insert into the table. These happen to be the 9 books that are on my desk at home. These are on my read list, which I haven't made enough progress on recently, which is why it keeps growing. Then we'll go ahead and we'll start a transaction. We'll insert our 9 books, and then we'll commit that transaction. So there's not a lot here. In a production environment, of course, this whole set of code would probably not be here. But I would want a singleton to represent my embedded database engine. And then I will go to my book class. So this is when I built this microservice, I was really thinking about an e-commerce website and probably a bookstore. And how would I start to go about building some services? And maybe I'll start with my product catalog, right? And provide a set of microservices for letting someone browse that catalog. So the book, some simple properties, right? Name, author, category, the number of pages, and then you see these annotations at the top. These are the annotations that are part of the newer client that I'm working on to help make it easier from a development point of view. So you just do 2 things. Specify the database and table, of course. Then you specify your fields, which is really not much more than kind of a bean property name, the column name, the column type, and then as well as the indexes. So FairCom DB does expect tables to have indexes for the different queries it runs. So I have some fairly simple ones and 1 additional compound index. But otherwise, other than extending, persistent record, it's just a regular book object. There's nothing too fancy in here. And then we'll go to the books resource, which is where everything's happening. So this is, my REST service. My path is /catalog, you saw previously, and then /books. To get started, I'm going to go ahead and inject my database engine, and then I just have a set of methods, which are fairly simple right now, but one that gets all books. So session.getRecords, book.class. I have another one that will retrieve a book by its ID, which will look in a minute. So /catalog, /books, /ID, and then the ID. And this just does session.getRecord from this database, from this table. Here's the ID, and here's the type of object I want returned, which is a book. And then another one, this is going to look fairly similar, but this time around, we're going to create a filter. So we have this record filter class. We're going to get an instance of it, specify the database in the table, and then we'll add some filters. This one's pretty straightforward, but we want to filter by the name of our book. And then get records, we pass it the filter and the object type. And then this category, it's actually quite the same, right? We get another record filter. We then add a new comparison, which is the category, and then get all the records that match that filter, return them as books. So not a lot of code for the most part. I think it's fairly straightforward. So now we'll go ahead and we'll do two things here. Oh, I think my target directory is empty, so we'll go ahead and run this. So I'm just using the Quarkus dev to fire it up here. So now we have our microservice up and running. Come back to the browser here. So here's one. So this is just all the books that are in the database, the 9 that I loaded right on start of my singleton. Here's another one, /catalog /books, and then a typo in there, ID. Try that. So this will be getting our book by ID. Here's this, we'll do it a couple times. 2, 3, and here's another one. We had /catalog /books /category / maybe space opera is one. That's sci-fi. And so there are some of the books matching sci-fi. I think I started changing the category names a little bit earlier. But as you can see, there wasn't a lot of code to write. If we go back to idea here for just a minute, all we really had to do was create a database singleton, start that engine, get a session, which is really a connection to the engine, if you will. And then we were free to start using that engine, although we do it through our session, right? So db.get session, we can start doing session.get records, and we'll add session.update record, update records. But in this model, all of this is local. So for our Maven project, it's actually in this data directory. So these are actually the database files that are being created. And at the bottom, you can see the TBL books DAT file and the TBL books IDX file. So this microservice is running with FairCom DB, is an embedded database engine. It happens to be disk-based, although we could have created in-memory tables. And then all we had to do was just get a hold of that engine, create the appropriate model, in our case, because we're using annotations, and then we can just start interacting with the engine directly. No need to connect to a database, no need to create SQL queries. It's all available right there with the tip of your hands as a function. So I'm going to go back here to our presentation. So that brings us to the end. Thankfully, it looks like the demo gods accepted my sacrifice today, and our demo went fairly smooth, with the exception of that typo in the URL that I had to fix. But I think I'm kind of end here and see if we have any questions.
Awesome, Shane. Thank you so much for that presentation and demo. Attendees, if you do have questions for Shane, please go ahead and put them into the questions panel. And we do have a few here to get started with. And the first one for you, Shane, is, does FairCom DB support JSON?
It does. It's interesting. I think I often describe the API as a NoSQL API because quite literally it's not SQL based. Instead, you have objects, your database, table, index, field, record, and you make function calls to manipulate these. But like a lot of the NoSQL databases that you would typically kind of associate with, it does support JSON documents as well. It can index JSON fields, you can query JSON fields. So my examples in this microservice happen to be records and a bunch of discrete fields. They could have also been a JSON document, and I could have been working on that as well. The choice is certainly yours.
Okay, good to know. A follow-up question with you is FairCom DB free to use?
It is. If you want to give it a shot, which I encourage everyone to do, it's freely available for download on FairCom.com. It includes a developer's license, but also you're more than welcome to check out the GitHub repository, which I think maybe I should escape out of my presentation here. I'm not sure if I added a link in there for everyone, but it is at github.com. github.com/FairComLabs, and what you will see is this FC bookstore catalog project. So this is up to date. You can run any of these commands to get up and running. This project, as you saw when I was going through an idea, it does have all the necessary resources. So you actually have the embedded database library, and there's a developer license there as well. So absolutely free and easy to use and get started with, and I hope everybody tries it out.
Yeah, absolutely. That's a great resource to have. So make sure that you write that down, attendees, if you're looking to access FairCom's GitHub resources. Looks like we've got some more questions coming in for you here, Shane. First one reading, how do you deal with queries for multiple tables and individual microservices via API?
Yeah, that's a great question, and we didn't really touch onto it too much, but one of the architectures is tables can be in more than one microservice. So we had an example that we had been discussing internally. I think it had to do with orders. So typically in an e-commerce, you have your order and line item tables. They probably have a product SKU in there. And that SKU, of course, references a product that's probably in a separate products table. So I would say that that products table should be in both your product catalog microservice as well as your order microservice. The only difference is that the product catalog can only be the product table can only be modified through the product catalog microservice. Whereas for the purchase or order service, it's essentially a read-only copy to help make sure that things like foreign key constraints are all held accountable. So I suppose the short answer is you can absolutely have a table in different microservices, but I would avoid having different microservices writing to the same table. We still prefer scenario where each table is ultimately owned by a specific microservice, and then any writes go through it. That might have been a long-winded. Hopefully I got the answer for you, but if I didn't, feel free to rephrase it or ask it again, and I'll give it another shot.
Okay, awesome. Following up with another question here is, does FairCom DB work with Node.js?
It does. So I don't do as much with JavaScript these days as I used to in the past, but we do have a Node.js client. And if you're in the IoT space, we also support Node-RED.
Okay, great. Good to know. Another question here is, how does FairCom DB compare with MongoDB?
Yeah, so I'd say they're substantially different. Probably the key aspect of FairCom DB here today is that FairCom DB can be deployed as a database server or as an embedded database, whereas most other databases, including MongoDB, and correct me if I'm mistaken here on that one specifically, typically are not embedded within applications. They're not really built for that particular use case. So FairCom DB is a little bit unique, and that it also comes with a shared library that you can embed within applications. Beyond that, they're also a little bit different in that FairCom DB supports lots of different models, if you will. It's not engineered for a specific way of modeling your data. The most natural ways, of course, is records or JSON documents, but you can just as easily store images and then index byte offsets within those binary files. Certain image files, for example, the first 4 or 8 bytes in that file might tell you the height or width or some other characteristic of the image. You can actually tell FairCom DB to index specific byte ranges within a binary file. So it's much more flexible in that regard. And while it does support JSON, and you can index JSON properties and certainly query them, I don't know that I would call it a full-fledged document database, right? I mean, MongoDB is a very, very good document database. So yeah, I want to kind of kudos to both, right? I mean, Mongo is a great document database, FairCom DB, kind of a different deployment architecture, and it has support for JSON, but I suppose at the end of the day, I wouldn't call it a JSON or document database.
Okay, great. Thank you for that distinction. It's very important. Some more questions for you here, Shane. Is FairCom DB open source?
Yeah, so that's something we're working on right now. You might have caught it a little bit earlier when I was introduced, but I worked for MariaDB before this, Couchbase before that, and Red Hat, before Couchbase. So I have a long history of working at open source companies. My current priority right now is open sourcing our database clients. So that's kind of the first step for us. But we recognize the importance of open source, and I'm excited to be here to help the company navigate that space.
That's super exciting. Okay, let's go into some more. And this one has to do with embedded databases. And this reads, how do you suggest the frequency or syncing strategy for embedded databases with the database server? Is it configurable? And is the communication between them bidirectional?
Yeah, so there's 2 parts that are fairly straightforward and easy for me to answer. The latter one, yes, it can be bidirectional. That's up to you. The other one, I think before that, you can also choose whether you want it to be asynchronous or synchronous. So you have both of those choices from a configuration and deployment perspective. On the interval, I'm not sure that you can specify the interval. So I have to go back and look into that. But that was an interesting one. So if you're thinking batching, maybe where we just want to replicate batches of changes on a specific interval, I can look into it. I don't know the answer to that one specifically off the top of my head.
Totally okay. We will make sure that you get the attendees' contact info if that's something that you can reach out with some further answers post webinar.
Absolutely.
So, right. So I believe that is all the questions that we have for you today, as we are also running out of time. So with that, DZone would like to thank a big thank you to you, Shane, for your phenomenal presentation on microservices.
Thank you, and thank you everyone for joining us. I appreciate it.
Great. Again, DZone would like to thank FairCom for providing the audience with a great webinar. Lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Have a great day.